there'll be some things that we don't talk about. I'd say, I certainly won't say anything about the Nashville tornado, which is one of the more deadly tornadoes we've had in our country in a long time, maybe as many as 10 years, almost. So I was away this week and didn't pay any attention to any of the conditions associated with that event, so I'm not going to be able to say anything intelligent about it. We do have in the immediate forecast along the East Coast, we have an extraordinary cyclonic development about to occur. And so I will talk a little bit about the pieces that are coming together to conspire to produce that development. And then Michael will probably be talking about the forecast in a variety of different ways. So I hope to be able to show you some interesting things. This would have been a perfect day to have this 5D ready, but it's just one of those things, I almost never travel, and the week I travel, the weather gets interesting. So I come in this morning and I had other things I had to catch up on. Sorry about that. So here's our week-long infrared satellite loop, and we're close to the end now. This is Tuesday, midday Tuesday, I think, right? So and I forget when exactly stuff went down in Nashville, but probably with this event right here, right? Yeah, there it is for sure. So that's not very nice. Tuesday night and Wednesday. Later into the week, so this is now Thursday, we're going to see, you don't really see anything obviously developing off the Atlantic coast, but you sure see this disturbance right here. And that thing has a manifestation currently in the satellite too. Low clouds, of course, you can see in there, higher clouds, circulation center. And these two are going to get their activated. Can you stop it at the last image, Pete, when we get there, just as a preview? You'll see a flare up of higher cloud, and we'll see in the radar in just a minute that that's not just high cloud. That's actually a reasonably heavy precipitation occurring right along the Delmarva Peninsula and down to northern North Carolina. Here's the upper disturbance of interest, and there's something not so well formed off the Carolina coast, and the combination of these two things, how they get their act together, will be part of what we talk about in the discussion today. So, and when they do, at least the forecast in the very near term suggests an extraordinary development is about to occur. So that will be quite interesting to look at that. And this might be one of the first diabatic elements that ties those two disparate circulations together and drives them toward each other in what could be a historic development.
Yeah, again, just a couple of things. So that area of low clouds that you see over, that passed over us last night, you had the really gusty winds. We had a wind advisory last night that I don't think was, at least initially wasn't anticipated, but we certainly got some strong gusts if people were awake or were awakened by the strong gusts. But associated with a really potent upper trough, and this is, for those of you in 311 or 452, 453 now, that low cloud swirl that you see there is a manifestation, and one way you could understand it, it's this strong geostrophic circulation over a lower boundary. So it's Ekman pumping, forcing this low cloud, maybe a moist enough boundary layer, you can lift air, you get some low clouds forming around that, but that's a really potent upper trough. And then there's some evidence, I guess, in that cloud streak you see across Florida into the South Atlantic. I don't know if that's the edge of the tropical jet or an old front that's out there. That's another baroclinic boundary along which some initial development, as John said, has occurred, but it's sort of waiting for this next upper trough to pick it up and take it away. So
yeah, and the great thing about these developments is that, of course, if you have a potent disturbance over the continent, snow covered or not at this time of year, it doesn't make a great amount of difference, but the stability of the column in this region is not as low as it is right off the coast. So these things are literally going to explode when they get into air that can be moved easily in the vertical, and then everything goes crazy. And they're getting a head start here, and I don't know how yet. Maybe we'll learn a little bit more about this today, but this reminds me a lot of the diabatic initial start for the November 2019 event. That was a clear frontogenetic signal in that storm, as far as I understand it to this point. And that developed a really local plume of intense vertical motion, a lot of diabatic heating, started to erode the upper PV and drove a fairly substantial downstream development. This might be related to that, same kind of general picture, but we'll have to wait and see as it plays out. But it's really going to be an interesting storm. And I think you're right, this is kind of a trailing baroclinic cloud. You can see there's elements of cloudiness that are continuous all the way to northeastern Arizona. So that does look, New Mexico, that does look like it's probably a frontal type region.
And that initial development had its origins to an upper trough that moved down the west coast of the United States. Yeah, or even further, maybe back over the Carolinas, it's actually kind of weakened now, but it had its origins to an upper trough that moved down, cut off the southwestern part of the United States, and then moved into the across the continent. So you can actually see that upper trough over Texas.
Oh yeah, it's been a parade of them this week. The subtropical jet last Friday was just straight across the whole continent and into Gulf of Mexico, in one of its odd configurations we've seen a few times over the last few years. Okay, so maybe we should just jump into looking at the phasing and the current structure and the phasing of those two disturbances. So let's start by looking at our local in time visible loop. So it starts to, a few more elements of this structure start to emerge here. I mean, one thing you can see for sure is that this cloudiness over the Delmarva Peninsula and just offshore does not appear to be only high clouds. That looks like thick convective clouds. So even before looking at the radar, one gets the impression that's a substantial diabatic impact being levied by that cloud mass. And it does also look like this whole cloudiness that we saw in the colored infrared is clearly tied to something that looks like a frontal zone. And then we can also see cloud elements racing eastward or northeastward, and probably at high elevation, and that's probably indicative of a strong subtropical jet. So all of this stuff is occurring poleward of the subtropical jet, maybe even in an exit region of it. I just don't know. We'll see when we look at the upper level.
John, I can mention that the subtropical jet, which is kind of along the Gulf Coast, there is
So about like
it's
this.
an old subtropical jet. Doesn't have much of a
Just here.
off of Mexico. That one's a good subtropical jet.
Okay. So there's a gap between two maybe jetlets within this flow. Huh?
Yeah.
Yeah. Okay. We'll see that when we go to the upper level charts, if how well that's replicated in the poorly observed region here. Let's take a look at the water vapor peaks. So that sometimes can show us some things at upper levels that are interesting. Yeah. So when I go to the upper level charts now, I'm going to be quite interested to see what kind of structure do I see running from eastern Lake Superior down along the Indiana-Illinois border down to about far northeastern Tennessee. I'll bet you it's a strong upper baroclinic zone and a hook in the PV. If we can see that in some of the other analyses, that'll be the way it looks. This does look like the beginning of a development region down sheer of a strong upper PV feature, although it doesn't on the satellite. On the visible satellite, one might not draw that conclusion. But seeing this dark spot indicative of low water vapor content in the upper troposphere, probably historical subsidence is related to that, and that historical subsidence has driven the high PV from the lower stratosphere into the upper troposphere. So that's the condition that we're probably going to see in terms of developmental ingredients at upper levels. So really quite an interesting situation just from a scant look at a couple of different analyses right here. So let's now take a look at the radar over the eastern United States. And here, as you can see, this is substantial precipitation. This is widespread 40 to 45 dBz precipitation just off the Jersey Shore and then over Delaware and parts of Maryland. And then open cellular convection here in what presumably then is quite cold air aloft. So we'll see if that's the case. You don't often see it like this. I don't see it over the continent. And so maybe minus 30-ish or minus 32 air or something like that at 500 millibars in western Pennsylvania and over West Virginia. And then immediately down sheer of that, this explosion of cloud head. And you might remember from the satellite picture that that's only a few hours old. That only started developing a couple of hours ago, and it's just exploded. And, it's a barrier to see any other, well-organized precipitation. We'll see when we go to the West Coast what that's tied to. But one can even see within these elements in the open cellular convection, one can see a sense of a circulation center. Looks like it's right over Rochester or Buffalo, or close to it, right here in far western New York State. But then a really interesting open cellular convection over the high terrain of the Appalachians. I don't know how many times I've seen it.
John, I can point out you in the previous one, you just showed that in western Wisconsin, Subsidence Street.
Right in here, yeah.
That seems to be associated with a polar jet that might be taking a drink from the polar night jet because they're crossing up there to the north.
Okay.
And we've seen before when they cross, it seems to have some effect downstream or upstream. But downstream right now, I think you're getting that folding of the tropopause because of something that this little polar jet picked up from the polar night jet as it's coming south. So there's something going on up there, but it's interesting that the tropical push is not that great at this point.
Yeah.
They will come together
Yeah.
at a later time, but right now they're not doing it. But this connection with the polar night jet, which I keep noticing, this semester particularly, seems to be happening right now.
Well, I don't understand it enough to
I don't
say that I
either,
have an alternative explanation. Maybe it's a complementary explanation that I have ready to suggest why the tropopause is being forced rapidly downward. And, but there might be connections to things that are well above the tropopause itself that are influencing that.
In looking at previous things like this, I noticed there's big folds when you have this northerly flow that arches down from the polar night jet, from underneath the polar night jet. This produces big folds. And I think when you look at the isotachs in the vertical, you can see there's a connection, that these two jets are somehow related to each other when they cross each other. And whatever that is, it seems to be happening here.
Yeah, okay, well, that's another example of that coincidence. So let's take a look now at some of our upper level charts, Pete. Let's start at 500 millibars. It'll be along exactly these lines that we'll be talking about. What are some of the mechanisms by which you're setting up this developmental environment? So here's the 500 millibar analysis from 7 o'clock this morning. It's a deep upper trough, and we saw in the satellite photo that circulation of that low cloud mass seemed to be centered around, northeastern Ohio or western New York State. We just saw that on the radar. So that's a little bit more current than this map. But this is a really intense, as Greg just pointed out, straight northerly flow southward towards, the base of this upper trough over Tennessee. And my eye is drawn to the extraordinary cold air advection that's going on in this lower left quadrant of that, or I guess over Kentucky and Tennessee. I've got 90 knots at Nashville, and I've got 20 at Cincinnati. So there's extraordinary cyclonic shear and strong cold advection. The consequence of that is that you have strong NVA by the thermal wind right over central Tennessee, and that's forcing great subsidence there. And presumably not just at 500 millibars, but all the way up to the tropopause and above. And so there's tremendous tropopause subsidence going on right in the base of this trough. If one were to look at a time series of 500 millibar vorticity, one would certainly see an increase as this tropopause subsidence is occurring on this transect. It's not going to occur all the way along this, however, because some of this region is characterized by warm advection cyclonic shear, which stuffs the tropopause back up the chimney, in a way. But it's only when it's cold advection cyclonic shear that you stuff it downward. But that's immediately upstream of that cloud and up shear, actually, too, because you can see the thermal wind as a proxy for thermal wind, the isotherms here at 500 millibar. It's up shear where we have that extraordinary development apparently going on right now in the cloud. So all of this stuff is really nicely tied together in a very nice little dynamical package. This 5D would be great to see some trajectories. I would initialize them. I'll just say what I would do if I had had the time. I would have initialized them in far eastern Tennessee, Knoxville area, see where they come from. Presumably they would have been just about parallel to this flow, but substantial subsidence along the trajectory would have been the case. And then you put a probe on there and see what the PV is doing, starting out in 2.5, and it's all the way to 2.5 at 500 millibars by the time you're down here. That's a really strong upper trough.
John,
Yeah.
with that subsidence in that circle vorticity, perhaps from Wisconsin down through southern Indiana, the fluids at the end of the end of that region, right, further to the west. You point out those two stations, Nashville, and then the one that's in
Cincinnati. Yeah.
So there, I'm wondering, does that help to round out, expand the structure of the vorticity?
Yeah,
so
I suppose it does, right? Because there's some stretching along the short axis of what would be a strip of vorticity. One could imagine if you had a pen, it would be really nice if we had one of those things you could draw on this map. But you could have a little ellipsoidal strip of vorticity with the largest values down at the end. I think we'll see that when we look in just a minute. But Michael's question is, if there's strong difluent stretching deformation at the end, then you're kind of changing the geometry of that feature from mostly linear to a little bit more isotropic at the end. And that's definitely going to lend itself to greater development. It's easier to have a widespread region of PVA. From the PV superposition point of view, you've got the more isotropic you make your disturbance, the more the circulations add together and so on. So yeah, from every perspective that I know of, that's another important piece of the puzzle here, yeah. And it's quite subtle, but that's right. In fact, that was a characteristic of the Erica IOP explosive developments. In fact, I was just staying with Gary Light.
Right, exactly.
Gary's work was showing that this deformation in the large scale flow is really important at the last
So
step.
it's that initial barotropic deformation preceding the actual cycle.
Yeah, that's right. So here's something for what we're working on. Maybe the subtlety of changing the initial conditions could be that it manifests a little bit stronger deformation downstream.
Right.
That might be something to keep our eyes on, to make the thing a little more isotropic when it unfolds out of the northwesterly flow. So let's take a look now a little bit higher first, and then we'll go to 850. So let's start at 300 millibars and see what we have there. So here's a really nice example of what Greg's talking about. Here's probably a subtropical jet, I'm gonna guess. We can determine that by going higher. This is a little bit of the weaker portion of that subtropical jet over Texas and parts of northern Mexico. A more substantial looking feature, not greatly substantial at 300 millibars down there. So we're maybe a little too low. Here's the polar jet, where in the exit regions right in this location, for ascent descent, it's really being maximized on the trajectory towards Tennessee. And that's quite an interesting situation. It's not the strongest jet, but it's got all the right configurations of temperature advection and curvature at the base of it and so on. So it's all perfect. Let's go to 200 millibars. So you notice the higher you go, you get out of the jet core region for the polar jet feature. And this is now characterized, this whole flow is characterized by cold advection in the lower stratosphere along the entire length of where the polar jet is. And so let's see, cold advection in anicyclonic shear does the same thing to this substance going right through the jet core that's starting in the lower stratosphere. And then here's slightly higher wind speeds. This is kind of, as Greg points out, kind of a weak, monolithic, old subtropical jet. There's the gap over Texas, and this is a much more substantial feature that's further to the west. So I don't know, if one were to just be given a couple of these upper level maps at random, if someone were conspiring to fool you, it wouldn't be hard to fool you today. That why is this thing going to be such an extraordinary development? It's not exactly apparent to me. Some of the elements are, but not the whole thing. Huh?
When's the development going to be?
Today,
12 hours.
12 to 18 hours. Yeah, so it's imminent. And so you'd say, why is that? I mean, sure, it's a nicely curved upper trough. It's got a pretty decent upper front from what we can tell here. I mean, if we were able to dissect some other data sets, which we'll do in a minute, we might learn more. But you know, it's not the most dramatic upper development I've ever seen. I wouldn't expect 30 millibars of deepening in 6 hours in the next 12 hours. I wouldn't expect it. Okay, let's go to 850, and then we'll go to pivotal. No, tropical tidbits, because we look at cross sections. This is maybe the most informative map of all of them, in my opinion, because it shows the two ingredient structures that are trying to get their act together. Here's the quite weak disturbance off of the Carolina coast, so weak that it hardly shows up in a circulation feature in the clouds because it's really in the lower troposphere. And it arguably is not even evident at all the lower tropospheric levels. And here is an equally weak looking disturbance at 850 over the eastern Great Lakes. It's weak here because I think the structure is stronger aloft. So you're kind of penetrating down into relatively cold air and the circulation gets a little bit weaker. The thermal field at 850 is robust, but not well organized. It's widespread cold advection all the way from the border of Kentucky and Tennessee, all the way. It's like Sherman's march to the sea, except it's cold air. And there's no interruption of that march, just like then. And so, but not really organized into a strong frontal type structure. There's probably weak frontogenesis along here, and that maybe accounts for the higher clouds and weak precipitation we saw in the radar over southern and central Florida. So a little stronger frontogenesis out to sea.
So, and that cold advection over Tennessee, Kentucky, those areas in the northern Alabama and Georgia, that's helping to force height faults in the mid-trough.
Oh yes,
right. So we also have that. So that's helping to deepen the trough just.
That's right. Yeah.
Just a little bit.
Because the cold advection gets weaker as you go higher. Yeah,
right.
That's right. It's concentrated in the lower troposphere. And here's the region of the cloud head development, which is actually right between the two disturbances. And so that's interesting. One might expect it's out here. It's not. It's right there. So very interesting is that. Okay, let's, and it's going to get warm in the weekend. Here's part of the reason we get this lee side feature developing along the whole spine of the Canadian and U.S. Rockies. It's really warm in southwestern Saskatchewan. And it's going to be quite warm in the warm advection region and bone dry dew point temperatures of 16 or 20 degrees, so extraordinarily dry air in the subsidence region. But it'll warm right up. It's going to be 70 or so in Boulder on tomorrow. 70. It's ridiculous.
Should we look at surface and lightning as well?
Yeah. Let's do those two things. And then I want to go to tropical, and I want to show you my vertical motion diagnostics too for fun.
If you want to focus in on the northeast or mid-Atlantic.
Yeah, so this is good. So we've got snowing in Pittsburgh, and then everywhere to the north and west, wherever it's precipitating, it's mostly snow. That includes Cleveland and what's this? Maybe that's Pittsburgh, right?
Yeah,
that's Harrisburg. And then rain along the coast. So a lot of the precipitation is going to start and stay as rain. It's quite warm. It's in the 50s, mid 50s and 60s in North Carolina. And then it's in the mid-40s uniformly along the coast, all the way from, actually even from Portland, it's 42 there, and it's all the way down to 48 at Norfolk. So it's really warm along the coast. And it's currently, at least in these odds, light rain, but I wouldn't be surprised if there's a few local downpours or at least moderate rain showers in this region. But this is the cloud head that's developing at the current time. And then along the southern coast, the dew points are low, indicative of the fact that this weaker circulation off the coast has dropped cold air all the way down to the sea in Georgia, and the dew points are in the low 30s. So these are nice days in Georgia. Atlanta's 54 over 29. That's a rare day in Atlanta. People rejoice when that happens down there. So that's a really great day to enjoy down there. And then, let's see, we're 34 over 17. Pretty hard to argue with that. It's a nice day. Right now, it's in the mid-50s or low 60s in the plains of Colorado, the immediate lee side of the high terrain, and flow a little bit off the terrain. And so
South Dakota's looking
it's
pretty
to stay warmer. Yeah, the banana belt in South Dakota has temperatures in the mid-50s, 64 just on south of the border into Nebraska. So just to the east of Rapid City, they do call it the banana belt. That's a place that's routinely warmer than anywhere else at that latitude or broad longitude sector because of the hills. And the only other place that we saw it was raining is up in the Pacific Northwest. A little bit of light rain to the south of Seattle, and then some near Portland. Probably more widespread than those odds to pick.
If we could go back to the Northeast for just a moment. Another interesting thing, temperatures are relatively warm. Dew points, at least from southern Pennsylvania, southward of the above freezing. But there is some dry air to the north. And if you look over parts of
Albany
State,
47 over 24. Yeah.
I think, so the low to mid 20s. Not super dry and cold, but it's there. And if that air could be tapped, you could imagine bringing down this evaporational cooling with significant upward vertical motion. Conspire to, turn any areas there that are rain to snow later today. That's a cyclone deep.
That is a good point. The wet belt temperature is somewhere in between these two all the time. So it's, maybe around 30, 32. And then if you have ice in there, it's lower than that. So it's possible that you get some interesting local thermodynamic effects from the precipitation shield once it really gets cranky. And it's already, I think these odds are understating what's probably happening in the region. I bet it's more than light rain in a couple of those places, or borderline light to moderate. A lot of nice pressure falls too. In the region where the cloud head seems to be developing, they're not uniformly in the 2.5 millibar range for 3 hours, but some of them are right along the coast, a little further north than I might expect, and minus 3.5 millibars at Provincetown.
4.4.
Huh? Oh, 4.4 at Martha's Vineyard. What's going on there, or in the Antarctic? So that's interesting. It's a broad region of pressure falls up in this location, so things are happening. Okay, let's go to tropical tidbits, people. Oh, it's starting to look like something.
Yeah.
Okay, we've already seen that, though. We don't need to see it again, but let's go to some forecast model stuff. And then let us take a look at initial conditions. So let's go to 0 hour, if it's a 12Z run. Yeah, it is. So, they don't have the initial time? It's okay, we can take 6 hour forecast. I'm happy with that. And what I'd like to do is, I'd rather do this less blindly than I'm doing it, but let's cut right through here and see what the structure of this thing is.
Control, right?
Yeah, control, and then you drag, yeah. Is it control? Yeah. Yeah. Okay, great.
Also, if you change the field, you can go to the initial time. It's just the preset fields aren't valid.
Oh, yeah, okay, that's right.
Okay, you want to do that?
No, let's try this. This is okay. So let's take a look at the potential vorticity along that cross section. As I say, it's a little blind, but we have an idea where the upper baroclinic zone was, so that's why I was trying to draw. Yeah, that looks pretty nice, doesn't it? So there's A and there's B. So there's the southern station and here's the northern one. So here's 100 and not jet, maybe 110, trying to squeak out there. And then here's the upper front. These are every 5 degrees, so we got 295, 300, and 290 as this bunch of isotropes that come down to the top of the boundary layer, down over the southern south coast of Texas. And there's the 1.5, I think it is, or the 2.0 PVU surface, 2 PVU. So it gets all the way down to 700 millibars or 650. That's pretty good. So that's a pretty deeply penetrating tropopause fold. And polar and subtropical jets, they're not coincident in the vertical in this case, not at this time. So that's a pretty decent upper tropopause structure right beneath the jet core. And let's take a look at the, it's too bad we can't wait, you can have all kinds of variables. Let's take a look at the frontogenesis theta E and omega. So I'll leave this right there. That's where the jet core is. Let's put it back like that. And try to see. So here's the baroclinic zone. These are the theta E isotopes, and a couple of isotherms. And omega shaded is subsidence. Is that right?
Yeah.
Okay, so there's subsidence just about through the jet core. It's a little bit displaced exactly from the jet core. This is ascent, that's descent. So just what one expects in the vicinity of such a tropopause structure. So there's been historic and current subsidence right along this set of isotopes, and that's driving the tropopause downward, and we see that high PV. So before we quit, let's just get a horizontal view of that at this time as an initial condition, nearly initial condition, of something like PV or upper vorticity over the same domain. Yeah, so here's the upper PV. This is the pressure at 2 PVU. So the lower the pressure that's down here in the blues, that means you've got a really depressed tropopause. And then these greens reflect the tropopause value PV is much higher than that. So this is and we cut a cross section right through there just a minute ago. So here's the fist of God coming down from high latitudes and driving the development over the Delmarva Peninsula. It's just a perfect setup for that. And even higher PVs, that is lower elevation of the 2 PVU surface down in eastern North Carolina. That's immediately up shear of where the development's occurring. So this is dramatic. What one would do in a research mode is initialize some air parcel trajectories right along this strip, see where they came from and how much they've subsided, and then try and ascribe physical mechanisms for that subsidence. I think they're going to be related to the cold advection and cyclonic shear broadly. So this is a really nice upper development. And you can see how isolated the depression in the tropopause is. You go from pressures around 300 or 250 millibars down to 600 in no space at all. That peak, we're here. Let's take a look at that. Yeah, that's going to be nice. And then we'll do the PV. Come on, don't fail me now. That's pretty nice. So that's a knife-like vortex structure that comes all the way down to 750 millibars. And over here, we're at above 200. So that's subtropical subtropical tropopause, and the polar tropopause goes down to 700 millibars with a wind speed max of about 130 knots right in there. So that's beautiful. And we might as well do omega, just so we know where this is. We're going to probably have a little bit of subsidence through the jet core still. We're not looking at the big vertical motions. I'll save that for another time. So there's the subsidence through the jet core. Really nice. So that's great. Okay, one last thing I want to show is my QG omega. So this is a storm that's probably nowhere close to a low Rossby number, but at some of these things. But you can still, the quasi-geostrophic system is pretty robust. You know, if you walk around and only use it when the Rossby number is 0.1, that's foolish. It's pretty robust. So let's take a look at the 12Z. We'll start right here, Pete. I don't know if my 12Z comes in on time anymore. I haven't been paying attention. This is a 700 millibar vertical motion from a 12-hour forecast valid this morning at 7 a.m. So where it's blue, it's subsiding, and where it's yellow, it's ascending. And this is a solution to the total QG omega equation. So these are every decipascal per second, which is about a microbar per second. So this is on the order of like 6 subsidence and strong, equally strong ascent. And the dotted lines are 500 and 900 millibar thickness. And so one gets the impression that right here over Tennessee, the subsidence is on the warm side of that thickness gradient, and that's exactly what you need to keep developing the upper front. We just saw it's a pretty robust structure. And immediately down shear of that, you're going to have positive vorticity advection by the thermal wind, and that accounts for the ascent to a large extent. I can prove that that's the case by partitioning this total vertical motion field into the 2 pieces. One that is by the PVA, by the thermal wind predominantly, the other one that's by frontogenesis. So let's look at the shear-wise part of this next, Pete, and that's right here. So this is only a fraction of that, but it sure looks exactly the same. Not the same intensity, and then also a slightly more cartoony distribution of the subsidence. But broadly speaking, the shear-wise part of the vertical motion is running the show this morning at 7 a.m. Not entirely, though, because let's look at the frontogenetic piece, which the QG system does not handle well naturally. It's not going to be good at frontal type vertical motion, but you even see pieces of it. Here's some frontal subsidence, here's some frontal ascent. And this 7 hours, or how many hours? 5 hours before the development of the cloud head. That seems to be what's driving it. This is displaced a little to the west because of the timing. Let's go to 18Z and look at this same panel. And that's right there. Yeah, so there's the That's frontogenetic ascent that's being forced and not well captured by the QG system. But even the fraction that is exactly coincident with where that heavy precipitation is busted out. And that's pretty neat. And in fact, I'll keep my pointer right there over the Delmarva Peninsula. Let's go to the shearwise as the other component at this time. And that's also pretty large, but it doesn't have the same geometry. So this geometry and the ascent that's going on here might account for some of those higher pressure faults we saw further north. So this is setting the storm up, but it's really a nice picture. And the last thing I want to show you is, I don't know which time it is. Let's go to the total at 24 hours. I think it might be the next one. Not this one, yeah. This is extraordinary. I can't even count how many are in there. Let's go to 30 hours. And this is just south of Cape Cod and the Islands. First time I've ever seen it. I don't have enough contour intervals available in GEMPAC to get to the center of this thing. It's not like this is a broad region of uniform ascent, just like this one's not a broad region of uniform descent. I've just maxed it. I've maxed out 30 contours each, I think you get. So it's got to be at least 30 centimeters, roughly 30 centimeters per second. And here's Massachusetts, Cape Cod, so it's just offshore, and this is where the extraordinary development is going on that Mike is going to talk about. So, and you can still see this strong upper frontal structure that's probably still driving the tropopause downward, but it's now somewhat divorced from where the development's occurring, because there's probably a big balled up PV structure right in here, and that's enough to produce this couplet of strong vertical motion.
So that would show up in the shearwise, right?
Yeah, that's right.
See that?
Let's do that. Let's see what the shearwise looks like at 30 hours. Yeah, it's pretty much the whole thing. And since we're here, we might as well do the frontogenetic part. And that's pretty nice, but only in one spot, right there at the development core. One other thing we can do, let's go to the shearwise again, Pete, and I'll do one more split. And that is, so starting here, this is not entirely the vorticity advection by the thermal wind, but boy, it's like 90% of it in almost every case. So what we can do is actually figure out how much of this comes from the vorticity advection by the thermal wind. So let's go to the Sutcliffe term, which is 30 hours. This is only PVA, NVA by the thermal wind. So it looks the same, it's a little more cartoony. Then we can split it up. How much of this comes from shear vorticity advection, this couplet, how much from curvature vorticity advection. So let's do that. Let's do the shear vorticity advection first. And that's not quite the same distribution. And then curvature is the other one. And that's down there 30 hours. So that's, the geometry is preserved in the curvature. So my first guess is that this storm, at this stage in its life cycle, is being driven predominantly by the curvature in the flow. And there might be other ways to try and diagnose that, but this is one way to make some statement about that in an initial glance. So that's interesting. And it's not always the case. Some storms have exactly the opposite predominance of one or the other.
So if it's driven by the curvature, does that also mean then that the sort of a classic early dynamics intro to identifying divergence patterns at upper levels with a change in curvature being associated with divergence convergence because of the change in the flows turning? Does that mean that's the big piece of it, or can you relate it to that?
I think you can relate it to that. That's what Kate's working on. We're trying to see whether or not in cases like this, not specifically what she's working on, but broadly speaking, in such a case, it would be interesting to do a partition of the total ageostrophic divergence. Find out, is it largely a long flow direction changes that drive it, or a long flow speed changes? I would have my suspicions alerted that it's a long flow direction change that drive it. And if that weren't the case, that would be an interesting counter result. So, yeah. So anyway, that's where this thing's going. I don't want to give up any more information. I'm already 30 hours into the future, and you can tell it's going to be something big here, but I'm going to let Michael take over. So.
Okay. I was just going to talk about today's weather. That's
yeah. Yeah. Right.
Can we go to lightning for a second? One of the things I want to first just look at, because this is such a interesting development that's occurring, to see if we actually have any lightning strikes off the East Coast. One of the things that John was showing in his omega diagnostics, I'm wondering if the only way you're going to get omegas of that sort aren't going to be through just pure dry dynamics. It must be a reduction in stratification.
Yeah, it's going to be.
That's occurring there that does that. And so you can see here on the old Barclinic zone, well offshore, there's some lightning strikes that are showing up. But near where we have our nascent cyclone, just off, to the east of Wallops Island, Virginia, this morning and early this afternoon, we're beginning to get a few lightning strikes out there, and I think that's probably going to continue to get well populated. Just speaking of lightning, it has nothing to do directly with this case, but I guess there's a neat piece by one of our former graduates, Jason Seminow, or from his group from the Capital Weather Gang, that talked about a severe thunderstorm warning that was issued for DC earlier this week without lightning and with hardly any rain occurring. They had a frontal passage go by with some thunderstorms, and then later on in the evening, around 10 or 11 at night in DC, I think this was either Tuesday or Wednesday night, they actually got wind gust up to 60 miles an hour with decaying showers. They had this classic inverted V profile of the sounding. So that might be an interesting 453 type case.
So you're saying they had thunder but no rain, so that's a
That's correct.
thunderstorm?
Yeah.
Yeah.
Actually, no lightning or anything. No, it's not a thunderstorm.
That's all it came with that storm was.
No, there's no thunder. There's no thunder.
Oh, I thought you said there was.
It was a
Sorry.
severe thunderstorm warning.
Oh,
without
okay,
a
okay.
actual thunderstorm.
I'm sorry, I had it
Pretty rare,
backwards.
yeah. So, I wouldn't screw up on that. Okay, let's go to Salt and AOS. I would say to you, quickly looking at today's weather, and I'm going to focus immediately our attention to the developing cycle off the East Coast.
I should just say one thing, Michael. I did misspeak. My solver does not take into account varying static stability. It uses a uniform static stability. In nature, you're right. There's going to be tremendous influence of that, but it does not show up in my
Oh,
solver.
it's just used like a standard atmosphere.
Yeah, I use a standard atmosphere. So those
That's-
vertical motions are forced through a standard atmosphere.
Pure dynamic. That's
Yeah, it's unbelievable.
So as always, quickly, just for the weather here this weekend, for those of you that are out here, and welcome to all the visiting prospective students. This is a kind of traditional discussion that we have. This is just an old run, or a run from really old version of the MM5 from years ago, but it's like to do that because John liked these meteorograms.
I love meteor.
Temperature, dew point, and this is accumulated precipitation. So just like as John was saying earlier to me, this is our third weekend in a row that we've actually had the warmest weather of the week occurring during the weekend. And so this has actually been going to be quite nice. This weekend looks like it'll be dry and warming temperatures up. Again, the scale is in degrees Celsius. Wouldn't focus too much on that. We'll probably be into the 50s, I think, this weekend, certainly near it. And we'll check out the moss at the end of this. So let's look at the time night section. Again, it's pretty quiet over us, so I'm not going to focus a lot on that. But you can see the
Wow, it is
yeah,
boring,
the departing tropopause that was over us earlier, that lower tropopause has gone up high, so we're now well within, that trough moves off to the east. Again, this is time down here. This is height, our pressures are vertical coordinate, log pressure, theta in yellow, and you can see the horizontal winds here. And see that strong southerly flow that's going to develop during the day tomorrow and continue into early Sunday morning. Additionally, you can see the wall mix layer that forms over the course of this afternoon, today, and during tomorrow. So light northerly winds behind that trough that's departing, let things switch around midnight tonight with a southerly wind, and we warm up. You can see the isotrope sort of sliding downward, pretending a warmer weekend that's coming up. So this is really the nice weather coming up for us over this weekend. It's dry. Let's quickly go to the at 6 hours, okay, 0 hours of forecast. We saw this already, just a beautiful upper trough, right? Classic structure to a nice upper trough. If you did a cross section for it, we've already looked at some elements of it on the side. That John looked at, just well developed upper trough. Again, you can't get more classic than that. Let's go ahead 12 hours in the forecast, and we'll see how this begins to evolve. And again, one of the interesting things to note, we'll do an animation in a moment, is this nice sort of how the structure of the upper trough is not getting deformed. And you can see before we didn't see these purples and these very light blue colors right here that are emerging. This is a direct consequence of the fact that we know that if we're looking at potential vorticity, we're on an isentropic surface. Wind should simply affect this along, and we're good. We can explain all the changes in the maps purely from horizontal advection of PV along the isentropic surface. The fact that we're seeing a creation of these very low values, in fact, values that are below zero, is linked to the fact that we're seeing evidence of PV redistribution, with latent heating likely being the culprit in reducing this potential vorticity. The other option would be friction, but we're certainly high enough up that that's not going to be an issue. So latent heating is going to play a big driver in this. And it's going to do a number of things. One, from just thinking about how the upper trough is going to be ultimately informed when you look at the height fields, helping to build a ridge. So that's sort of this self-development type process that's occurring. It's halting the progress of this, the wavelength getting shorter. We get more robust vertical motions associated with that. This is really creating a situation where you have really strong PV advection now downstream of this. If we went back to the 6 hour image, you're not seeing these strong advections. If you just briefly go back to that 6 hour forecast or the 0 hour forecast. This is the 6 hour forecast, but you can see we're already at this time beginning to see the first evidence of that erosion of potential vorticity just ahead of the dynamical tropopause as it's arriving. And then if we step ahead 12 hours, you'll see that you get those purples there that weren't there before. Okay, well downstream of this as air comes up and then it's immediately turns anticyclonically and heads downstream, forming a nice strong jet well downstream of this, so forming a jet entrance region down roughly in this region. That's helping to take mass out of the column and helping with the deepening of the storm. If we go ahead one more time beyond this to 24 hours tomorrow morning, and then you can see that this PV is just, it can't be forced back to the, it can't just head out to sea. It's actually being halted because of diabatic redistribution of PV and the erosion of that advancing upper trough. So things sort of stay in place. This is a really nice development. And again, there's strong evidence from looking at this sequence of maps that diabatic processes are playing a big role in it. So how deep does this get and what's the future of this? We'll look at the GFS, but I want to look at just a really curious simulation that we get from the North American model. If we go to Pivotal, the 3-kilometer run of that, I don't know if that's available in Tropical Tidbits, but let's go to Pivotal. And I've looked at this. We'll select the 3-kilometer North American model. And we're starting right this time. This is at 995 hectopascal. We saw that, beginning to show up. Here's that nice plume of precipitation that's associated with the approach of that upper trough. Again, diabatic heat is occurring. You can even see some heavier precipitation. And we now know there's some lightning from thunderstorms actually occurring offshore at this point. If we go ahead on just 3 hours to 9 hours of forecast, we went from, I just missed them. We started off with 995 down to 980. That's 15 millibars in 3 hours. So this is really, as John was saying, this thing is just beginning to go to town in terms of expanding. Notice also, as the heights begin to crash, thickness is crashing here. You probably have a very strong, we look at surface winds in just a moment, strong ageotropic winds with these rapid pressure falls here. You're going to have an isobar component of the wind that's directed from the north and northwest of these regions, dragging down some of that colder, presumably drier air, also with strong ascent cooling the column. This is going to force some of this liquid precipitation to become frozen. That's at 980. Let's go ahead 3 more hours. You can't get much deeper than that, right? Well, yeah, I can. Here's another 15 millibars in 3 hours. Now, again, couple things, and just from John's discussion earlier, not all the elements seem to be here for this to drive the most, a sort of a storm that's almost maybe historical or potentially historical one that's going to be talked about a lot. If this were to verify, this would be certainly a very impressive storm.
Yeah.
But this is one model. We'll look at a couple of the models that don't deepen it quite as much, but still significant deepening, and deepening rates a little bit, the profile's a little bit shallower than this. But this is pretty impressive, and I don't know what could possibly go wrong with this. I haven't looked at this carefully enough before discussion today to see what parts could pull this apart, but there's a lot of evidence that things are coming together to produce, or will come together, at least for something that's consistent with a strongly deepening storm.
Would be fun to play what-if experiments. Oh, wait a minute. That's what we're going to do. Yeah.
Project funded to actually look at how the changing structure of the upper trough affects the deepening profile in terms of pressure as a function of time for these storms. Let's go ahead, just one more click, please, Pete, to 15 hours of the forecast. So 3Z this evening, 962, 3 more millibars. And we just click a few more just to let's get into the 950, 959.
Wow.
Look at that nice warm core that begins to emerge right here. This guy's smiling. He likes it.
Yeah.
959. So we have a really intense storm. Northern shield of it has snowfall associated with it. Before we look at some other model runs and look at some other diagnostics with jump back, I'd like to just go back, keeping this. Let's just go back in time from a model that was initialized, let's say 0Z last night. Don't leave the cyclone there. Okay.
Wow.
So the cyclone shifted a little bit. Do that again. Let's go to 24 hours off the coast. There has been, if you look, at least in some sense, if you keep moving the initialization time for the model forward in time from yesterday and a couple days ago until now, a slow shift to the northwest in general with this development. And so I think, for folks that are forecasting from, from Wakefield, Virginia, that has responsibility for the lower eastern shore of Maryland and southern Virginia, up through Philadelphia area that has responsibilities for New Jersey and parts of Delaware, all the way up into, I guess, just southern New England. This is something that, while the models are still forecasting this to move out to sea, it's getting, I guess, nervously close, or I would be nervous, as it gets a little bit closer in terms of the rapid development. And often we see when these storms deepen rapidly, they look a little bit to the left of the forecast track. So that's something to watch for. Let's go back to the current forecast, please.
I think it's true, especially in these storms that are strongly dynamically forced, because some of the dynamical forcing finds itself constantly in the northwest quadrant of the storm, and that's the strong PVA by the thermal wind path. And it's hard to move from that center of gravity.
Right.
And if it gets established and it's enhanced by the heating that's going on right over Delmarva right now, that's going to be a tug to the west.
Yeah, and that's actually, in fact, let's look at the 0303, the very first time in the forecast cycle right here. So we have this broad area of this broad cyclonic circulation. This analysis has the low back through here, but you have this broad cyclonic circulation. I'll just keep this here if we go ahead 6 hours. And some of the model forecasts, okay, so it advances northward. Some of the initial model forecasts actually were developing the cyclone further to the west, to the east, and then as the upper trough swung around, it kind of moved westward, appeared to retrograde. I think that's just this filling, and the strongest pressure falls were out just to the east of the upper trough as it advances offshore. Let's go to just the regular NAM, 12Z NAM.
All this snow is wasted on the fish, as
Okay,
Lance
so it's
says.
right here.
And Lance Bosat will be our robot speaker in a couple of weeks. I wouldn't be surprised he talks about this a little bit.
Excellent. So let's look at the vertical motion, so the upper dynamics. And this is things that you don't typically see with this, 700 millibars for vertical velocity. And you can see it's almost, not almost, it's saturated in terms of vertical motion.
60%.
So this is just absolutely incredible. So we have 700 millibars of mid-tropospheric, mid to lower tropospheric, strong vertical motion just above the surface. And that's kind of just yells at you, thinking dynamically about the intensification of this, the stretching term, right? What's happening with the stretching term in the lower troposphere? How co-located it is with the cyclone center in terms of fostering development. So we can actually look at that on we'll quit on this for a second and go to the terminal. And let's run that, say G-date time equals F03. So this is using GEMPAC. This is using the NAM data, the ADA model data NAM data from today. We'll run this. This shows sea level, this shows 1,000 hectopascal heights. This is perhaps just below ground. Here are the winds plotted with this as well. And then we're going to be applying the stretching term. I have it at a certain level, so we'll have to advance forward. Let's do G-date time equals F06. This will be roughly this time period. First of all, see heights falling. That's consistent with the development of this. And you can also see that the forcing for vertical motion. So this is that product. It's minus the absolute vorticity times the divergence. That's the vorticity stretching term in the classic baryclonic vorticity equation, right on the western edge of where the lowest heights are. So this is a region where that favors the further development of cyclonic vorticity in this region. If you invert that out, that's going to give you also height falls occurring on the western edge of this. So while this cyclone might have the tendency or the desire, if you will, if you want to give it some agency that wants to out to the east, it's sort of forced to be tugged back here on the western edge of it to just stay kind of in place before it races out to sea. Let's go ahead another 3 hours.
Yeah, that's the essence of baryclonic instability, isn't it?
Yeah. Everything's coming together with this. And you can see now we're almost co-located with the largest height falls and the observed height. These are the observed heights, and the generation of vorticity here. You can see this little region that extends out to the east, which is along the warm front, which we'll see in a moment as well. But nice frontogenesis that's occurring here, which is also helping to intensify this. But notice on that western side, the cyclone hasn't really moved that far. Another 3 hours ahead, you'll see the stretching is continuing right over the lowest heights. So this is really fostering a nice development. And one of the reasons we get this extreme development. So, well, look at that. And we can go maybe one more. I think it's just doing some time. I know we can do this as a loop. But just in place. And this is actually drifting a little bit to the north or so. So this is really going to be a pretty intense cyclone development right offshore of the vortex, stretching occurring just in the location you'd love to see it. And that leads to this really dramatic development. These things are nicely in phase. If we change our G function, G-func equals THTA, scale equals 0, and cent equals 3, and we'll do G-date time equals F00-F15. We can also look at just the thermal structure of this developing cyclone. And you can see the nice sort of maybe almost a seclusion that's forming. We can do
Yeah.
a semicolon L to loop it. And you can also notice just, this developing warm front right here, a nice frontogenesis right here. This would, you would also expect to see the nice swath of precipitation, which we've seen in the forecast, just on the northern edge of that developing cyclone. So this is just incredible with the development. So we know that the NAM at very high resolution gets us down to 960, let's say, to be not as generous as the model is doing. We can stop this for a moment, Pete. We can click on that and GPN it so we exit Genvec gracefully. You always want to do that, GPN. I know some places, if you come from a different school, they say GPN, now it's GPN. That's how we say it here in Wisconsin. Right, Zoe? All right, we didn't know your opinion. Okay, let's go to the Eastern WF model. Let's see how that's doing with its evolution for this, and we'll go back to the surface. Of course, it doesn't have ice thickness contours on it, so this is its forecast for this time, 993. It has that nice little region of precipitation to the north. We'll go ahead to 6 hours of the forecast.
I'm really curious about that precipitation region. I have a feeling it keeps the cyclone in the right spot to benefit from the stretching for a long enough time that they get in sync. I wonder if that's part of the story.
Or is it because the cyclone's there, it doesn't move much, so that you get the precipitation stuff?
Yeah, it could be the other way around. It doesn't look like it's connected that much to the cyclone though at the
Right.
initial stage, like right now. It looks like it's kind of an afterthought.
Yeah.
But I think it's the dynamic glue that keeps that thing in the right spot.
Could be.
I wonder if that's right.
So from 993 to 972, so it's what? Just
21.
about 21 millibars, or 21 millibars in 6 hours. That's not too bad. It's not as dramatic as the NAM. I love more than 21 millibars. It's a dime a dozen, right? Let's go ahead another 6 hours, 18 hours in the forecast, 970 to 961. So ultimately, even though the deepening profile is not exactly the same as the NAM, it does get it to this 960 region. And again, if we were to go back in the forecast, the initialization time, let's go back just 12 hours each time. 969, it's not as deep. And do that again. It's still actually in this sequence of runs. Go back again.
Is the timing just different?
It could also be a timing issue as well, but how quickly it moves out.
But the sensible weather is very similar until this panel. There were,
Yeah.
the heavy snow was just off the coast of Massachusetts and
Right.
south of Sable Island, just exactly in the same spot.
Look at the sea level pressure.
Yeah, it's unbelievable.
There's no contour like that. What is that? Right, so we go back to the current current initialization.
Makes you forget about the
And then let's
tropics.
look at the GFS finally. Okay, 964.
Mhm.
So all roughly in that low to mid 960 range with a really intense cyclone. Again, the track of this, there's been some, maybe subtle and maybe it's not as obvious as I thought it was to the northwest. And so again, I guess if people were forecasting for areas of southeastern New England, particularly Nantucket and Block Island, Martha's Vineyard, you might be concerned about about snow and wind for a bit this evening, early tomorrow morning. I guess the last thing to do is we can just step forward. We can take the GFS forward a little bit, just look over the weather for our area. Again, this is tomorrow. This is late tonight, midnight tonight. Don't forget also when your clock's ahead on Sunday morning.
Can I just ask, is there a significant wave height forecast in Pivotal?
Good question.
I don't know either. Somebody makes that, but I don't know which one it is. Anyway, I don't want to slow you down.
Yeah, it might be that. Yeah, I don't think
That would be
it's-
interesting to look at on this thing.
Listen, there will be waves and they will be big.
It's true.
30 yards. That's out to sea.
Oh,
And then here comes the warmth for us, much requested, much desired warmth, the big warm up for us. That's Sunday, tomorrow night into Sunday, early Sunday morning. Nice, modest warm advection, but looks like a nice weekend coming up.
Wow, what do you think the high is going to be with 555 thickness?
I'd go probably I'll predict Moss. I've not looked at it, say 57.
I'll say 62.
And Pete, the answer is in weather. So unfortunately rain on Monday, so it's obviously a nice weekend. This is perfect. UAV in. And
58, you're right.
58, that was closest. Not by a note.
Except by a degree.
57. I was closer to the forecast last number. That's like a prices, race rule or whatever. And then our next chance of rain coming in perhaps on Monday. But again, the big story is going to be this development off the East Coast. It's going to look pretty nice in the satellite imagery, I imagine. And we want to do it since we've got 168 hours, so a week from now, next weather watch, we pull off. Again, if you want to believe it, I'm just looking at this really rapidly. And then we go ahead one more week, or almost a week, to during spring break.
Whoa.
Once we return from spring break, we go back to winter again. If this is to be believed, but I don't know. Everyone likes that. John likes it to see more snow come in.
I want to
John
see some more. You know, today is the March 6th on 1732. There was the Great New England Colonial High Tide. And then in March 6th, 1962, there was the Great Atlantic Storm that went all the way from Miami up to Massachusetts. So I mean, these things happen on March 6th. That's weird, isn't it? That's weird.
Anyway, well, thank you, John, for a wonderful discussion, and thanks everyone for participating. Thanks, Pete, for running everything, and have a great weekend.
Thanks, Mike. Yeah. How many of you are visiting graduate students?